All right, let's talk about the periodic table. You know the one, that huge, kind of intimidating chart of, well, everything. It looks super complex, right? But what if I told you its biggest, most powerful secret is actually dead simple? It's not buried in the tiny details, it's all about one great divide.
Seriously, the best way to think about it isn't as some boring list. It's more like a treasure map for the entire universe. See, it organizes every single element in a way that lets scientists see these hidden patterns. They can even predict how different substances will react before they even touch a test tube. It's pretty wild.
And, like any good map, it's got a key. And this key is super simple, but it unlocks a huge piece of the puzzle for understanding chemistry. It's one of those secrets that's been hiding in plain sight the whole time. And bam, there it is. This one simple line creates this great divide. It basically splits almost every element into two big teams. You've got your metals and you've got your nonmetals. And believe me, this isn't just some random line they drew on the chart. It's probably the most fundamental, most powerful way to classify anything in chemistry. And as you can probably tell, one of these teams is, well, it's huge. We're talking about 80% of all the known elements, they're metals. The nonmetals only make up that other 20%. But don't let their small numbers fool you. They are incredibly important. I mean, the very oxygen we're breathing right now, yep, that's a nonmetal. Okay, so since metals are basically running the show on this chart, let's get to know them a bit better. What is a metal anyway? What does that even mean?
Well, it really all starts with location. Location, location. As a general rule, you're going to find all the metals on the left side and smack dab in the middle of the periodic table. Their spot on the map is like the first big clue to who they are, and it tells us they're all going to share a bunch of the same traits.
So what are these traits? Just picture a classic metal in your head. It's shiny, right? It's also probably malleable, which is just a fancy way of saying you can bend it or hammer it into a different shape without it breaking. They're amazing at conducting heat and electricity, they're usually solid, and they're sonorous. Yeah, that's the cool science word for that satisfying ding sound a metal makes when you hit it. Think of a bell, And this is where it all clicks into place. These aren't just random facts for a science test. These properties are the reason we use metals the way we do. Copper is a fantastic electrical conductor? Great, let's make all our wires out of it. Iron and aluminum conduct heat like champs? Perfect, they're now our pots and pans. Gold and silver are shiny and easy to shape? You guessed it, jewelry. It's a total perfect match between what something is and what we do with it. All right, so that's Team Metal, the big players. But what about the other guys, the ones on the other side of that great divide? Let's meet the opposition, the nonmetals. So if the metals are camped out on the left and in the middle, it probably won't surprise you to hear that the nonmetals are hanging out on the right side of the table. And just like their address is the opposite, a lot of their properties are too. Let's do a quick head-to-head, right? Metals are shiny, nonmetals are usually pretty dull. Metals are amazing conductors. Nonmetals are terrible conductors. That's why we call them insulators. Metals are bendy and strong. Nonmetals are brittle. You hit them, they shatter. And while most metals are solid, a ton of nonmetals are actually gases or liquids. They're basically polar opposites in almost every way. So things seem pretty clear-cut, don't they? Left side metal, right side nonmetal. Shiny versus dull, strong versus brittle. Easy peasy. But, in science, rules are, well, they're often more like guidelines. So do all the elements play by these rules? Oh, absolutely not. Some elements just seem to love breaking the rules, and honestly, that's where chemistry gets really interesting. Okay, first up, let's meet mercury. It's sitting right there in the metal section of the periodic table. No question about it. But it breaks one of the biggest rules of being a metal. It's not a solid. At room temperature, mercury is a liquid. Yeah, its melting point is a crazy low -38.8 degrees Celsius. So why do we still call it a metal? Well, because it still acts like one in other ways. It's still a fantastic conductor of heat, for example. And when it gets warmer, it expands in a really predictable way, which is exactly why it was perfect for those old-school glass thermometers. It's a rule breaker for sure, but it's still on Team Metal. Now let's look at a rebel from the other team. Carbon. It's a nonmetal through and through, but in some of its forms, it starts acting a lot like a metal. I mean, think about a diamond. That's pure carbon. It's incredibly shiny and has a super high melting point. Those are two very metal-like traits. Or, hey, take another form of carbon. Graphite, the stuff in your pencil lead. It can actually conduct electricity, it's got that shiny look to it, and its melting point is through the roof. All classic metal stuff. But it's also brittle. Snap a pencil lead and you'll see what I mean. That's a classic non-metal property. So carbon is kind of having an identity crisis, borrowing a little bit from both teams. And this really gets to the main point here. Figuring out if something's a metal or a non-metal isn't as simple as checking one box. It's more like you're a detective. You have to look at all the evidence. Does it have most of the properties of a metal? Okay, then we'll put it on the metal team. It's all about weighing the different characteristics and seeing which side wins out. And that leaves us with a really cool thought, right? This whole great divide between metals and nonmetals is a super useful tool. But it's the exceptions, the rule breakers, where the most fascinating science really happens. It kind of makes you wonder, doesn't it? What other simple rules in science are out there, just waiting for someone to come along and find the one thing that doesn't fit?